Welcome to Scatterplots for Chemistry. Most of the data that we will graph will be in a scatterplot, and it's useful because it shows us the changes from the independent variable acting on the dependent variable. The slope can give us the rate of change if there is time involved, and it's useful for trends. Our graph really helps us predict data that's not on the graph. If we go outside of our data, for example, if we look here, that's extrapolated, same thing over here, outside of the data. And then if we're looking within the data along two points and we're predicting in between them, then that's interpolate. Some guidelines that we will be following all year. Our graph needs to have a title, and it needs to tell us the independent and dependent variable and some sort of relationship. Two examples, the dependent of blank on blank and the effect of blank on blank, are very useful. Sometimes you might need a key. Typically in our lab notebook, we won't use colors, but we will use symbols. Graph should always be on graph paper. Luckily, our notebooks are graph paper. If we are using OneNote, there's graphic backgrounds available. Make sure that you are using a straight edge. So if you're making the graph in your lab notebook, a ruler, the edge of something else that's straight, and when you're making it in OneNote, you can use the line tool. The axes should be labeled. So the label should tell what it is and then the unit. We put the independent variable on the x-axis, the dependent variable on the y-axis. The only exception of this is time always goes on the x-axis. Your graph should fill the available space. So the graph should take up in your lab notebook at least half of the page, and you need to make sure that the data fills the graph area. So for example, if this first one was turned in, I would put a mark like this, meaning that it didn't reach the half page mark. Here the axes are half page, but the data doesn't fill it, and so I will do something like this to show. Here we have a graph that's half the page and the data is spread out on the graph. Each scale should be consistent. If one box is a year at the beginning, then one box always represents a year. The range of each one may be different. So here we have seconds, and over here we have a very small measurement, 1 times 10 to the negative third is each block. You have to feel a scale that's going to expand your data to fill up the graph. Scales do not need to start at 0. The origin does not have to be 0. In other classes that may be true, but in chemistry that doesn't work very well. It's easier to read if you use multiples of 1, 2, or 5. Make sure you label it every so often. Doesn't have to be every square, but maybe every 2 squares. And again, each square should have both a label and a unit. We haven't talked about significant figures. We will in Chapter 2, and that has to do with precision. So you can't lose or add precision, so you can't add or lose digits. Your numbers on the graph should have the same number of significant digits that the data had. Many times we're drawing a best fit line or curve. It is most important here, do not connect the dots. They're not absolute numbers, it's an experiment, so they're not going to fall precisely on a line or a curve like they often do in your math class. So we draw a straight line or a curve that best represents the tendency. It doesn't have to go through the origin. Lots of times it will not. Don't extend it beyond or put arrows on. It just represents the data that you have. So you do not want to end your line this way. No arrows on the end. Here are some examples of lines of best fit. I would expect you to be able to draw straight lines of best fit, but the curves, I will tell you if the data is supposed to curve so that you know to make a curve. If I'm looking at this, okay, first of all, for some problems, this is connect the dots, so we don't want that. Here, right, we have a graph that doesn't fill the space. Okay. Same here. And so when you're analyzing graphs, you have to make sure you're comparing the scale. For example, this graph is the same data, but looks very different. For our purposes, we want to spread the data out so we can see the trends. Here are some common mistakes. Here are examples of common mistakes. If we're looking at the scale, this represents 1, 1, 2, and 4. So that's not a consistent scale. Over here we have the same thing. We have 5, 10, and then 10. Also, we have connected the dots. Again, we have our scale is not consistent. We have one block representing 5 and the next one representing 10. Sometimes you'll have a direct relationship. Sometimes that's called positive correlation. We increase one variable, the other variable increases as well. The negative correlation, the indirect, sometimes it's called an inverse relationship. When one variable increases, the other decreases. With the direct relationship, we have a positive slope. With the indirect relationship, we have a negative slope. Sometimes you will hear proportional, and proportional is when the ratio of x to y, x divided by y, or the inverse gives a constant number. This is a linear relationship that has to go through the origin. It's not very common in chemistry. Remember I said you do not have to put your line of best fit through the origin, and the origin does not have to be 0. An indirect proportional rate is when one value decreases at the same rate another increases. A hyperbola. Pause the video and try the problems on the next page. Let's take a look and decide if the data is proportional. Here we have how many hours in miles. Okay. One way is to take the miles divided by the hours, miles per hour, and it is 65 miles per hour for all three of these. The ratio is, so yes, this is proportional. If we look at the cost per pounds, does it give you any kind of a discount if you buy more pounds? So here we have 3 is 225. Doing some quick math, if I double my x, I've doubled y. If I've tripled x, I've tripled y. We can do the math, and so it's 0.75 cents per pound all the way through, so this is proportional. Another miles per hour, and if I divide those, I find that each one is 6 miles per hour depending on the hours, so I can say yes, this is proportional. Label the following as direct, indirect, and then the second part is proportional, not proportional. Look at this one. We have a positive slope. It is direct. If I increase one x, I increase a half of y, another x, another half of y. And so this one is direct and it is not proportional. It does not go through the origin. Here I have an indirect relationship and it is not proportional as well. Looking at number of days and the number of clay figurines that are painted. All right, so I have a positive slope, so I know that it is direct. It goes through the origin, and every time that I increase 1x, it goes up 5y each time, and so this is both direct and proportional. Lastly, we have a negative slope. It decreases. as the length increases, so I know that it is a indirect. It's also a hyperbola, and so it is proportional.